Hi everyone and welcome back to my YouTube channel. We'll be beginning with a new tutorial which is specialized for mathematical inequalities. Just like the functional equation tutorial that is on my YouTube channel, we'll be also starting with a similar one but on inequalities. So if you're preparing for Math Olympiad inequalities, let's say your Math Olympiad, your country's Math Olympiad, or for IMO or any similar such contest, or even if you just want to level up your mathematical inequalities skills, then you have come to the right place. So basically our plan is simple. We'll be covering the main inequalities that you need to know. For example, the AMGM, the Cauchy-Schwarz, the holders, and all the famous inequalities. And of course, the additional techniques and tricks that you need, and will appear a lot in Math Olympiad contests. We'll be dealing with all of that. And the strategy for each lesson is simple. We'll just introduce the theorem, try to provide a proof, then go with easy examples first, and level up until we solve IMO difficulty problems. So, what are we waiting for? Let's get started. Before we start with our first lesson, I would like to talk a little about the history of inequalities in Math Olympiad, or the IMO specifically. So, when the IMO started in 1959, inequalities were really important. So, like in each, in each year, we will expect one problem. Of course, like not necessarily each year, but for example, if you just look at the first IMOs, you will see lots of inequalities appearing. So basically, inequalities were really important. But later on, actually, suddenly inequalities disappeared from IMO. So if you just open recent years, like maybe 2010 till perhaps something like 2018, you will not see that much of mathematical inequalities there. Instead, you will see just the algebra questions. Most of them are either functional equations or like some other topic. So people really started ignoring training for mathematical inequalities, and instead will focus on functional equations or any other things like sequences or something else. But guess what? Just suddenly, in the recent years, inequalities appeared in the IMO, and people or students were caught by surprise, as they weren't preparing that much for inequalities. And hence, right now, if you are preparing for Math Olympiad, you really need to develop your mathematical inequalities and just train on it, just like any other algebra topic. For example, functional equations or polynomials or anything like that. And that's why we'll simply begin by uploading this high quality Math Olympiad tutorial on inequalities in particular. So basically our first lesson will focus on the AMGM, which is the arithmetic mean geometric mean inequality. This inequality is really important, and you usually will see all Math Olympiad books will start with this inequality. It's basically the core of the inequalities that you will see in Math Olympiad. So let's start by introducing that. Before introducing the main theorem, I always like starting with a simple example, which is really a simple inequality, but it's suitable as an introduction. It's kind of a specific or a special case, a simple case for just two numbers of the AMGM. So let's say we want to prove for two non-negative numbers greater than or equal to 0, the following inequality: a plus b over 2 is greater than or equal to square root of ab. So give it a try and then keep watching. Basically, this is on the left hand side is simply the arithmetic mean, as you can see, a plus b over 2 for the two numbers. And this is the geometric mean, which is just the root. Here it's the like square root of the product of the two numbers. So as you can see, this is actually the AM-GM. The AM is greater than or equal to the GM of the two numbers. But how can we prove this? Well, first of all, let's simply multiply by 2 both sides. So our inequality is just like this. A plus b is greater than or equal to 2 root AB. And of course, if we move stuff to the left-hand side, this is the same as this. And if you just look at this, this should remind you of something nice. Look at it. Something minus 2 times first number, second number, plus something like the second number. But of course, here, like we've got something squared, here's something squared. So this is simply the same as the formula root a minus root b squared. And guess what? We're done, because of course any square number is non-negative, right? Hence, like, the proof is done. Of course, there's another way to prove this, which is simply like some people hate, let's say, roots, so they just end up squaring from the beginning. And this is not wrong. If you just square from the beginning, you will also get the same thing, but of course you will get actually a minus b squared is greater than or equal to 0. So both proofs work. Okay. So basically, as you can see, this is the AM-GM just for two numbers. Alright, let's actually solve one example, one problem on this, before presenting the main AM-GM. Okay. So now, we also want to prove for three numbers that are non-negative the following inequality: a square plus b square c square greater than or equal to ab plus bc plus ca. Okay. Before actually proving this, I want to really tell you something that you really need to keep in mind, because it's very important. We will be using it like in our basically in our course, and in general you should always try to use that as well. You'll see it in most of the Math Olympiad books, and it will really like save your time a lot, and like your proofs will be more efficient. Basically, we'll be introducing the sigma or the sum notation. So for example, let's say we have, okay, here three numbers: a square plus b square plus c square, and on the right hand side we have ab plus bc plus ca. Do we each time have to write a square plus b square plus c square and here ab plus bc plus ca? Actually, no. You can use just the sum notation. For example, we can represent the left hand side using sum a square. Of course, like it should be clear that we just have three numbers, because maybe if we have just two numbers, it will be just a square plus b square. Or if you have just four numbers, it will be a square plus b square plus c square plus d square. So it should be really clear that we have three numbers here. Then, of course, this sigma a square is just this left hand side. And what about the right hand side? You guessed it. It's just sum ab. So you immediately go ab plus bc plus ca. Alright, so this will really be beneficial for us, because it will save lots of like unnecessary writing, and saves lots of time. So I like most of the times I'll be just writing sigma a square or sigma ab or something like that. Of course, there is something that we'll also discuss, which is like the symmetric sums and the cyclic sums. Okay, so if we want to explain it right now, shortly, basically, if we have something that is cyclic sum, for example, let's say we have sum a square b, and we say this is cyclic sum. What does that mean? Of course, like we were working with 3 numbers, as we mentioned, 3 numbers here. That actually means this is a square b plus b square c plus c square a. What exactly are we doing? Imagine that we have like a circle here, and we have like kind of arrows going like this. So, okay, if we just look at this, what is it telling us? Like, how can we construct that this is this? Why don't we have, for example, a square c? Well, just follow here the arrows. So first of all, we write the first one, a square b, from here, copy it and put it here. Then we replace each letter, let's say, or each variable with the one next to it. For example, if here we had a square b, next, like a, should be replaced with b. So we replace it with b. Next, in the third term, we replaced b with what? With c. So we got c squared. So a squared, b squared, c squared. Same thing for b. b is replaced then with c and then with a. So this is basically the cyclic sum. By the way, like if you're using cyclic sum, you don't have to write cyclic sum. So if I don't write anything, then you should automatically assume I'm working with cyclic. Okay, then what is actually symmetric sum? Well, symmetric sum is something different. If I write something like this, then it's not cyclic anymore. Now I'll be using all different combinations. So now a square b plus a square c. Like, I'll be using everything. I'm not just going like in this circle. So I'll be using everything. A square b, a square c, b square a, b square c, c square a, c square b. So it's really like obvious the difference between the like both of these. Clearly here the sigma symmetric has 6 terms, while the cyclic has only 3 terms. That actually makes sense here because 3 factorial is just 6, and we're using all different combinations. So that's actually the difference between symmetric sums and cyclic sums. So if I don't write anything, then you should assume it's cyclic. But if I write symmetric, then like of course I can't like I need to specify it's symmetric so that you understand what's happening. And also another thing, if I wrote sigma symmetric a square, then you should be careful because this is not just a square plus b square plus c square. Actually, it is a square plus a square. So actually, like always, whenever you have a symmetric sum, then it must consist of 6 numbers actually, like 6 terms. So in fact, sigma symmetric a square is a square plus a square plus b square plus b square plus c square plus c square, which is simply actually 2 sigma a square, right? So as you can see here, the sigma symmetric a square is 2 times sigma a square, which is cyclic. Okay, so keep that in mind. Okay, but that might be confusing when you start with it, but you should accumulate with it because like you will face this a lot. So always keep that in mind. When you have a sigma symmetric, then you need to cover all n factorial combinations. Like you always have to have n factorial numbers or terms. Of course, on the other hand, when you have cyclic, then you're just going in one circle, so it's just n numbers instead. Okay, so keep that in mind. Another thing is that, of course, when I say sigma symmetric, it's different from describing this. For example, like if you're working here, if someone asks you, is this a symmetric? Is this expression a symmetric thing? The answer is no, it's not symmetric, because as we said, like we have a square b, but we don't have a square c. So if you like write something like f, like as function f a b c, then the function f is not symmetric, it's cyclic. However, this one here, if you said f a b c is this, then it's symmetric. But what if I asked you this here? If we said f a b c is sigma a b, is this one symmetric? Well, you might say that no, this is a cyclic sum, so it's not symmetric. But the answer is actually it is symmetric, because we're talking about the function, not the sigma. Like here, we have everything we need. We have AB, we have BC, we have CA. All of them are covered. So the function f is symmetric, but the sigma is not symmetric. Like the sigma, if we wrote symmetric, it will be double, like 2 times sigma AB. So it's a bit confusing, as I told you, but you really need to keep that in mind, because it will be very important for us to deal with like inequalities in general. Okay, so keep that in mind. So now let's actually just prove our inequality. Let's write it again. Now we just need to prove that. Okay, I'm not going to write sigma a square right now for like a certain purpose, as this is our like first lesson. So I'll be writing it all. So how can we prove this? As you know, the only tool that we've explained so far is the AMGM for 2 numbers. But here we have 3 numbers. How can we deal with that? Well, we have actually a very, very powerful idea here. Okay, you know what? Let's just pick 2 numbers and try to apply the AMGM on them. So a squared plus b squared is greater than or equal to what? We know that over 2 is greater than the square root of a squared b squared, which is just ab. In fact, like if we just multiply both sides by 2, it will be like this. Now that's interesting. We have this one and this one, right? But we have a squared plus b squared and we have 2ab. Well, what happens if we do the same for the others? B squared plus c squared is greater than or equal to 2bc. And c squared plus a squared is greater than or equal to 2ca. Guess what? Now, if we just add these 3 inequalities, we're done. Because now we'll get 2, and now actually we'll get 2 sigma a squared, and here 2 sigma ab. So basically, we can cancel the 2 and get our inequality. Okay, so this technique is really powerful. Like it's kind of called the pairing technique, because we're pairing. Like, okay, we need to get AB. How can we get AB? We need to pair A and B. So if we pair these, we got AB. Same thing for each, like BC. Pair these, we got it. Like you should always believe that once you get one of them, then like of course the others are the same, and then if you just take the sum of them, you're done. Like you must be done. Don't worry about it. Just worry about like getting, let's say, like pairing them up and getting rid of at least one. Okay, so this strategy is really powerful. By the way, like here we applied the AMGM for 2 numbers, but it's not on the root because we had them squared. So I really want to write here these 2 versions of the AMGM. So version 1 and version 2. Just for 2 numbers. We haven't presented the AMGM, the actual AMG. So for 2 numbers, we can write this: a squared plus b squared is greater than or equal to 2ab. We already just did that because, of course, a minus b squared is greater than or equal to 0. The other version is actually the same as AMGM. Remember, like we know this. So what happens if we square both sides? We'll have this, right? Okay, so these 2 seem like the same. However, they're a bit different, and each one has its own usage. It depends on the problem. Because, for example, let's say in a question they told you that a plus b is equal to 2. Then here, you know that ab is less than 1. You will not apply this. You apply this. But what if they told you that a squared plus b squared is equal, let's say, equal to 2? Then, of course, you will apply the first one. Okay, so keep that in mind. We have 2 versions. One links AB to the sum, and one links it to the sum of squares. Okay, so now let's move on and present the real AMGM, the generalized version. So, the generalized version is the following. Let's say we have n numbers, a1, a2, up to an, and they are non-negative numbers, then we have the following inequality. a1 plus a2 till an. We said it's the am, right? The arithmetic mean, or the average. That's it. What is the geometric mean? Simple. The nth root of the product. Okay? So the am is greater than or equal to the gm. That's it. Okay, so actually, as we mentioned, we'll be dealing with sigma, like in order to cancel time. We don't really want to spend lots of time like writing all of them, and here also writing all of them. So let's write it in a simpler way using the sum notation. So for example, the LHS is actually sum ai going from 1 till n over n, of course. And the right hand side, actually, the nth root. Okay, we don't want to use like the product a1, a2 up to an, so we'll just use the pi symbol. So the pi is the same as product, of course, going from 1 till n. Okay, perfect. So this is also the AMGM, written with just the symbols. Okay, so of course, some notes here. The numbers must be non-negative because of the roots thing. You need to keep that in mind. And like in general, you need to apply AMGM. The numbers should be non-negative because in some situations, let's say you're applying it for 3 numbers. You're saying this. If the numbers actually are all negative, it will be reversed. The reason is simple. Like, I'm not sure if you know this, but keep this in mind. This is really a powerful algebra trick that is very powerful. This can be factorized. If you move this to the left hand side, you can factorize it. So a cube plus b cube plus c cube minus 3abc. This is just the sum of the numbers times so what does that mean? Remember, we already worked with this. We said it's always positive. This is always positive. Actually, even if it was like the numbers are negative, all of them are negative, this is still positive. And I will leave it to you to check why. Like, try to work with this and see why it's always positive, even if the numbers are negative. Try using the same as our proof. But if this is positive, then that means this, the sign of this, is the same as the sign of this. So if all of the numbers are positive, then okay, the AMGM works for 3 numbers. This is positive, this is positive. So as indeed, this is correct. But if all of the numbers are negative, this is negative. Of course, if you add 3 negative numbers, you'll get a negative number, right? So this will be reversed. And hence, you need to always remember, you cannot apply AMGM if the numbers are negative. Keep that in mind. Generally speaking, of course. Okay, so this is the AMGM. How about we give it a proof? Of course, there are lots of proofs for the AMGM, as it's really famous, but we will just pick one that's really nice. We'll basically pick an idea using induction. However, the proof that we'll be discussing is not an ordinary induction. For example, you might be familiar with the induction going from n minus 1 to n. The induction that we'll be working with is not that. This unfortunately doesn't work. You can't try with it. We'll be using another type of induction, which is really kind of weird, but it's really nice. We'll be moving from n to 2n. Wait a minute, how are we going from n to 2n? Like, even if we can do that, so 1 will lead to 2, this will lead to 4, this will lead to 8, 16, and so on. Any power of 2, right? Okay, that doesn't solve the problem, right? We only proved it for powers of 2. Well, of course, this is not the whole proof. This is only the process 1, let's say. We have another process which is going down from n to n minus 1. So for example, now how can we cover 3? Easy. Because 4 is correct, we can use process 2 to cover 3. How can we cover 5? Well, easy. From 8, we can cover 7, and 7 covers 6, and 6 covers 5, and so on. In fact, like that means process 1, the only like usage for process 1 is just to give us like big values, right? Like if we go to infinity, then we use process 2 to go down till 1. So this idea is really cool, and let's see how we can prove the AMGM using this idea. So first of all, we'll begin with the first, let's say, first idea, first process, proving n to 2n. So we'll assume that the AMGM is correct for n numbers, and we'll be working with 2n numbers. Of course, like working with n equals 1 is really like simple, n equals 1 and 2. So we'll just be working with n and proving it for 2n. So let's do that. We want to prove the sum of AIs going from 1 till 2n over 2n is greater than or equal to 2n root by AI from 1 till 2n. Okay, I don't need like each time to write like I, because it's really clear. So how can we prove that? Of course, we need to use like the n case. So we'll be working with n numbers and another n numbers. We'll simply split it into two sums. Okay, this is easy. So this is equivalent to going from 1 to n and then from n plus 1 to 2n, and all of that over 2n. And you know what, like let's work from left hand, like just this is the LHS, and try to apply the AMGM, because remember we can apply it on any n numbers, so we can apply it on here and here. Okay, simply we'll be applying it. So if we apply the AMGM, then here we have n times nth root product AI from 1 to n, and here another n times nth root by AI going from n plus 1 till 2n. All of that is divided by 2n, and now of course the n cancels the n. So now actually this is just equal to plus this over 2, of course going from 1 to n and from n plus 1 to 2n. Now actually, if you think about it, how can we go from here to what we want here? The idea is really simple. Remember, here we have a 2. So why don't we apply the AMGM only for 2 numbers, right? Makes sense. So if we apply AMGM here for 2 numbers, here we applied AMGM for n numbers. But now if we just apply that, the 2 will cancel the 2, because this is the arithmetic mean. So we just have a big square root of this times this. Okay, this is what we want. They get mixed and we're done. All right, perfect. Okay, so process 1 is correct. Let's go for process 2. So now we want to go from n to n minus 1. All right, now if you think about it, we need to prove it for n minus 1 numbers, but we know it's true for n numbers. So we want to start with n numbers, but one number should be kind of fake. It's not a new number. It's like it's kind of a function of the n minus 1 numbers. So if you think about it, what should we use? Generally speaking, in inequalities, what is the useless number? Like the number that doesn't affect the inequality that much. If you think about it, it's usually the average. The average actually doesn't change like the quantity that much, right? So this will be like our strategy. So we'll be putting the numbers. Okay, these are the n minus 1 number, but what is the nth number? It's actually the average. So here the nth number is just the average. So guess what? Let's just write it using the sum notation. From 1 to n minus 1, these are our first n minus 1 numbers, and this will be our this is our nth number. Okay, remember, it's correct for any n number, so we'll be applying that. So here over n is greater than or equal to the nth root. Here you need to be careful, because remember, what are our numbers? a1, a2, a3 up to an. An minus 1. So it's actually pi of ai's from 1 till n minus 1. But now what is the missing thing? It's the nth number. And what is the nth number? It's all of that. This is one block. This is one number. Don't be fooled. It's not like a sum of numbers. So I just be putting that. Alright, so I know this is true. And I hope to show it's true for n minus 1. So basically, let's simply do some algebra, because as you can see, this is here, here, and here. So probably we can use some algebra tricks to play with that. So the left hand side, if you take this as a common factor, you can take this outside, and now we just have 1. Oh, actually, sorry, I made a mistake here. This should be n minus 1 here. It's n minus 1, because it's we said that this is the average, right? So okay, keeping that in mind, what is this? This actually is just n over n minus 1. But okay, that's cool. N cancels the n, so we just have over n minus 1. All right, perfect. So let's immediately write it over n minus 1. This is the left hand side. The right hand side, it's still this times this. Okay, now also we have something nice. This and this, they are the same. So let's cancel them. Okay, it's a bit confusing how we can cancel that, having the nth root here. So we'll just simply take both sides and raise them to the nth power. Okay, so now this is to the nth. And now we removed the root here. Okay, perfect. So now we can just cancel that. Okay, I'll be actually doing it from here, just here. I will be erasing this. Okay, perfect. Now what's the only thing that we need to do? Notice that this is really the AMGM that we are looking for, but we just need simply to take both sides to the n minus 1th root, and we'll be done. Notice this is the average, the arithmetic mean, and this is nothing more than nothing but the geometric mean, and we're done. All right, perfect. So that means we have shown the process 1 and process 2, and hence using induction, we're done. We can simply like go to a very like a big number, and then we can, using process 2, we can go till 1. Okay, perfect. So we've proved the AMGM, and that actually is enough for our first lesson. All right, so in this lesson we learned about the kind of we took an intro to inequalities. We said that the AMGM is really powerful inequality, and we just provided the AMGM first of all for 2 numbers, and then we took a special case, or sorry, like a special example on just the 2 numbers. We learned this technique of multiplying both sides by 2 and pairing stuff up, pairing things up, as we did, like a squared plus b squared with 2ab. And we also learned about the cyclic sum, the symmetric sums, and like I really want you to understand that, because it's very important in your mathematical mathematical inequalities journey. And we also discussed the AMGM, basically the main theorem, the generalized theorem, and of course we proved it using this nice induction proof, like going from n to 2n and from n to n minus 1. Just one thing I forgot to tell you, that is the equality case in the AMGM. Like in each inequality you have some equality case. Remember, we're just putting here greater than or equal to. So you really need to know when does the equality hold. So in the AMGM, it's really simple, when all the numbers are equal. So we can just write here with equality if and only if all numbers are equal. This will really help you later. We will see through other examples how does the equality case guide you to apply the correct AMGM and avoid bad applications for AMGM. Alright, my friends, so that ends our lesson for today. In the next lesson, we'll be simply dealing with some simple examples, and we'll be leveling up gradually to solve some harder and harder AMGM problems with some really powerful techniques that I'll be grouping for you. So I really hope you guys enjoyed this video. Please like, share, and subscribe to my channel, and see you guys in the next video.